Well, hello. How are you doing today? Are you ready to get started on this journey of BC calculus? I am. Well, let's jump right in. In the discussion of calculus, one of the most important topics that we need to understand is a limit. So, chapter 2, we're going to dive in and talk about limits, and then we'll end this chapter with a discussion on continuity. Now, limit is a new topic that you probably haven't been exposed to before. When we talk about limit, I want to use an illustration to kind of illustrate what we're going to do here. And so I have two letters. I have a number line here. I'm calling this A, and I'm going to call this B. The word of the day that we're going to talk about is the word closeness. Closeness. And the question I have for you is simply, is A close to B? Now, think about that for a little bit. You may want to pause the video just to think about that. But is A close to B? Well, that would depend upon a few things. Namely, where is A and where is B? I mean, on this number line, maybe they look close to each other. Maybe they don't look close to each other. And so what we want to do is maybe put some parameters around this. And so what if I told you that A was located at unit 2 and that B was located at a value of 15? Then the question is A close to B? Maybe, maybe not. What if we left A at 2 and then we put B at, let's add a 0 to this, 150, and actually let's add 2 zeros to this, 1500. We're on a number line, so let's say 0 is back here. Is A close to B? Maybe we may say, well, it's further away from A and B than it was before. Let's keep playing with the numbers. So let's change 1500. Let's change this down to the value of 3. Now, is A close to B? Same question. I don't know. It's closer than it was before, but maybe that's close, maybe that's not close. And then if we keep playing with these values, and let's make B at a value of maybe 2.0001, is A close to B? Well, we may say yes, we may say no, we may say it's closer than it was before. So then the question is, well, how close does A need to B in order for us to say that, yep, it is very close to it? Okay, because if you look at this, we can keep moving A all the way from the left side, closer and closer and closer and closer and closer to the right side. So the question is going to be, what is the definition of closeness? How close can I be to something in order for me to say with certainty, yeah, you're pretty close, all right? And so if you think about this, I can move A as close as I want to be as long as I'm not actually at the same location as B, okay? So the definition we're going to use for closeness is going to be this. So I want you to write this down. The definition of closeness is going to be this. A is close to B if A can get as close to B as possible without actually getting there. Okay? A is close to B if and only if A can get as close to B as possible without actually getting there or without actually touching it. Okay? And so that is going to be our foundation of this thing called a limit. We're going to be approaching a certain value. We don't really care about getting there, but we want to approach a certain value and get as close as we possibly can to it and see what effect that has on the actual function's y value. That's going to be our definition of closeness. Okay, now let's continue. So what is a limit? Now the notation that we need to be extremely familiar with is what's written down here. So LIM in this statement stands for limit. Okay, now there should be some things you are familiar with. So f of x is still a function, right? That's that function notation that you learned in pre-calculus. And then we have some other notation surrounding it. This is how you actually would read this statement here. This statement is read as the limit of of f of x, so this is our function symbol, the limit of f of x as x approaches a is equal to L, okay? And so that's how we read this. So when we see the limit of f of x with that x and that little arrow pointing to a, the way we read that is the limit of f of x as x approaches a is equal to L. So we're going to be answering questions like, well, what is the limit of a particular function, let's say x squared, as x approaches some value, let's say the value happens to be 2, it's going to be equal to what? And so our goal is going to be to answer this question, what is this limit going to actually be equal to? And what we're going to do, our strategy is we're going to let x get closer and closer and closer to the value of 2 inside the function of x squared, and then the answer is going to be a y value that comes out of the function x squared as x approaches 2. When we talk about limits, there are two different ways we can express a limit. There's something that's called a one-sided limit, and then there is something that's called a two-sided limit. Up to this point, we've been discussing two-sided limits. So the statement we just had on the previous slide, we had the limit of x squared as x approaches 2 is equal to some value. This is actually what we call a two-sided limit. Okay, so if we had a function x squared, okay, so let's draw this here. If we have a function x squared, and just the general shape of this curve looks roughly like this, it's a parabola that's curving up, and we want to know what is the limit as x approaches 2. Well, 2, let's put it right here. What we're actually saying is we're going to be approaching 2 from the left side and from the right side, is what this notation means. So we're asking, the question is this: as I approach 2 from the right side and as I approach 2 from the left side, we want to know what is the y value of the actual function. And if you look at the function, you can kind of figure out what the answer is going to be. In essence, as we plug in 2.1 and 2.05 and 2.005, this function is getting closer and closer and closer to what value? What value do you think it's getting closer and closer to? That value would be 4. Okay, as we plug in smaller and smaller numbers on the right side of this function. And the same will be true from the left side. As we approach 2 from the left side, well, we're riding this red curve from the left side, and as you get closer and closer to the value of 2, you're going to approach the value of 4. Okay, and that is how we're going to be evaluating our limits. So this right here is called a two-sided limit. It's called a two-sided limit, okay? Now, there is something called a one-sided limit, and as you can probably assume, we're only going to be approaching the value of x from one side. Here's what a one-sided limit looks like. I would write down the limit of x squared as x approaches 2. We're still going to be approaching 2, but this time I'm going to put a little positive symbol up here in the exponent position. What this is telling us is that, well, we're going to approach 2, but we're only going to approach 2 from which side do you think we're coming from? Well, when you think about positive, all the positive numbers are going to be on this side. Okay, so in essence, it's as if you're coming from positive infinity. You're going to be approaching 2 from positive infinity, and that's the only way we're going to approach 2. Okay, so the value of 2, put it back here, is right here. And we're asking, well, what happens to the y value? What happens to the function as we approach 2 only from one side? Only from one side, we would land on, well, the same value we landed on before. It would be 2. But this is called a one-sided limit. Okay, so the limit of x squared as x approaches 2, and we say from the right side is equal to 4. Okay? Well, likewise, we can approach from another side. We can approach from the left side. So we can say, what is the limit of x squared as x approaches 2? And if I want to approach from the other side, we will put a little negative symbol here, which indicates we are approaching from negative infinity. Okay? As you approach from negative infinity, okay, and we'll change colors here. Well, we're coming in, we're landing on 2 from the left side. So we're coming in from this side, from this side. And as you ride the red curve here, notice what the function is doing. It is still, for this particular function, as it approaches 2, the y value is still approaching 4. Okay, so the answer to the to the limit approaching from the left side would also be equal to 4. Okay, now, I know the answer has been 4 for the last 3 examples here. Please understand it's not always going to be the same number as you approach from the left or the right side. Okay, now some key things to note here as well. When we talk about limits, they either exist or they do not exist. Okay, so when we talk about limits and their answers, we're going to be asking the question, does the limit exist? Okay, or does not exist. Okay, and the symbol we use for does not exist is simply DNE. Okay, so this is huge here. So does this limit exist or does this limit not exist? Okay, if it exists, it will be equal to a finite number. So 2 or 4 or 12. Okay, if it doesn't exist, well, we'll explore this a little bit more, but it'll be something very strange going on. The answer won't be finite always for these scenarios here. So limits exist or do not exist. Now, this is in contrast to what you know about functions. Okay, when we talk about a function from pre-calculus and those earlier algebra classes, functions are either defined or they are undefined. Okay, so a function is, we say a function is defined at a particular value, or we say that the function is undefined. Okay, so this is very important. We want to make sure we're using the right notation, the right vocabulary when we talk about limits. So limits are not defined or undefined. They either exist, meaning there actually is a limit, or they do not exist, which means there is no limit. It's not actually approaching a particular value consistently. Functions, we don't say functions exist or do not exist. We say that functions are defined, or we say that functions are undefined. Okay. All right, last thing I want to talk about in this video is, well, what's going to be required for a function to actually exist? And it's going to be this. This is a very important theorem down here at the bottom, and it says this: a function f of x, it actually has a limit as x approaches c, so we're talking about a two-sided limit, if and only if the right hand and the left hand limits at c, they have to both exist and they have to be equal to the same value. Okay, here's what we're saying here. So look at this first limit expression here. This right here is our two-sided limit. So we're saying the limit of f of x as x approaches c from both sides, two-sided, right, is going to exist if these statements are true. The limit of f of x as x approaches c from the right side equals some value L. The limit of f of x as x approaches c from the left side is also equal to the value L, okay? Because, and this is very important, because the left hand limit and the right hand limit, because they exist and they're equal to the same value, what we say is that yes, the two-sided limit does exist and it's also equal to the same value L, okay? Let's let some of this sink in. And our next video, we're going to look at some problems. We're going to do some limits on the calculator, and then we're going to study some graphical limits.